Good morning, friends. Today, I like to discuss the AC bridges. This is the second part of AC circuits. This AC bridge is basically based on Wheatstone bridge. We are very much familiar with the Wheatstone bridge. That is, there are four resistances in the four arms, and a detector and source are connected into the diagonal arms of a square. So as shown in this case also, the Z1, Z2, Z3, Z4 are four impedances which are connected to the network along with the source, that is AC oblique DC, because the same position for source is there with a source impedance ZS and key. A detector is there in the diagonal BD. So A, B, C, D has four impedances and one impedance of source and other impedance of detector are shown in the figure. In this way, there are three loops forms, that is loop 1, loop 2, and here it is loop 3. In these three loops, we use the Cramer's rule, that is the use in case of the network analysis that we will discuss in the unit 4. And according to the Cramer's rule, the impedance equation, that is a matrix formulation, can be done on the basis of these equation. These are Z11I1 plus Z12I2 plus Z13I3 is equal to E1, Z21I1 plus Z22I2 plus Z23I3 is equal to E2, Z31I1 plus Z32I2 plus Z33I3 is equal to E3. So these are the three equations, and these equations have different values in the analysis part. For example, the E1 and E2 are 0 because these two loops has no source, and E3 has the finite loop. So the equation will simplify, but on the basis of simplification, the bridge is said to be balanced. A balanced bridge is the bridge in which there is no current in the detector arms. So current ID is 0 in impedance ZD. The balance condition thus we can derived from the Eber-Cramer's rule as Z2, Z3 is equal to Z1, Z4, or the famous Z1, Z2 upon Z3, Z4. This one is the balance condition, and along this balance condition, another important condition is sensitivity condition. And this sensitivity condition means the order of all the impedances attached in the Wheatstone bridge are same. That is, Z1 is equal to Z2 is equal to Z3 is equal to Z4 in order. In order means, suppose there are the resistance of 100 ohm, so all of them must be of the order of 100 ohm. If it is 1000 ohm, then it must be in case of the 1000 ohm. But in other cases, this will be different, and in different cases. So let us consider the three important bridges, that is Wien's bridge, Schering bridge, and Maxwell bridge, for determination of the capacitances and inductances. In the 12th standard, we used to determine the Wheatstone bridge for the determination of unknown resistance using post office box technique. Here we used for the capacitance and inductance. So the bridges has been designed for finding out the self-inductance of the coil, capacitance of this, and frequency along with the power factor of the given bridges. So let us consider first Wien's bridge. The Wien's bridge is also a part of the practical in semester 1 and 2. Right now we have given the assignment to our students in part semester 1, and few of the students have the Wien's bridge. And the project, practical project, for the practical project they have to discuss about the Wien's bridge. So Wien's bridge is the just bridge, and for the project you have to discuss about detailed theory about AC and network and the Wien's bridge. So here it is the uh, theory of the Wien's bridge, how to determine the capacitance of the given capacitor with the help of Wien's bridge method. So the bridge is used to find the capacity of the given capacitance with the help of other components. What are the other components? Other components are resistances and capacitances known. The bridge is arranged as in shown in the figure. Then impedance Z1, this impedance Z1 is equal to R1, this is R1 plus 1 upon j omega C. This is XC, impedance offered by capacitors. Then Z2 is equal to R2, this is the same, and Z3 is equal to R3 plus, again this is XC, this one is XC1, here it is XC3, so 1 upon j omega C2, and Z4 is R4, that R4 is given in this case. So the balance condition is given as Z1 upon Z2 is equal to Z3 upon Z4. So the substituting the value of various impedances in the balance condition, that is Z1 is R1 plus 1 upon j omega C1, and here it is R2, and this Z3 is nothing but R3 plus 1 upon j omega C3 R4. So again, by simplifying this equation, R1 upon R2 plus 1 upon j omega C1 R2 is equal to R3 upon R4 plus 1 upon j omega C3 R4. Equating real and imaginary parts, this ends two independent conditions for the bridge during the balance condition. So the real part of this equation is R1 upon R2 is equal to R3 upon R4. So the R1 can be written as R2 into R3 by R4, this equation. The imaginary part, we equate these imaginary equations, then we have 1 upon j C1 R1 is equal to 1 upon j C3 R4. So this j cancel, and we have this one is 1 upon C1 R2 is equal to 1 upon C3 R4. So C1 is equal to C3 R4 R2. And the power factor of the given circuit of the capacitor will be as cos phi is equal to omega C1 R1. This is nothing but R1 upon XC1. That is, we have to discuss, this is R1, and this is the value of the XC1 as the case of the circuit combination. So this part, and the other bridge is Schering bridge, and this Schering bridge is given as the capacitance C1 is series with R1, then R2, and then C3. Here it is R4, C4. So the impedances of Z1 is equal to R1 plus J 1 upon j omega C1. This is equation 1. Here it is, this is equation 2, R2. Here it is equation 3, and this is equation 4. Again, substituting these values Z1, Z2, Z3, Z4 in the impedance balance condition, and then we find this one is, here it is, R1 plus 1 upon j omega C1 R2 is equal to 1 upon j omega C3 upon R4. This is R4 R4 upon 1 plus j omega C4 R4. Now simplifying this equation, we have this kind of the expression, and simplify with these equations the real part and imaginary part equating from the previous cases, as we see C1 is equal to C3 R4 R2, and from the imaginary part equations we have R1 is equal to R2 C4 C3, and the power factor phi is 1. This is R1 plus this 1 plus j omega C1 square of this value in the if the case is simple. So the last one is Maxwell bridge. This bridge is used to determine the self-inductance of the coil. In the given coil, this L1 is the coil which self in inductance can be determined with R1 in the series connected. A to B arm, from B to C arm is R2, and A to D is R3, and there is no, here it is no C3, so no need at all. And then R4 and C4 are parallel. So the impedances are Z1. Z1 is equal to R1 plus j omega L. This is XL. XL is, this is XL. And here it is Z2 is equal to R2. Z3 is equal to R3. And Z4 is parallel combination of the resistance R4 and XC4. And that is R4 upon 1 plus j omega C4 R4. Substituting these value in the bridge balance condition, that is we get Z1 upon Z2 is equal to Z3 upon Z4. So Z1 is R1 plus j omega L R2 plus R3 upon R4 j omega C4 R4. And that is simplify R3 upon 1 plus j omega C4 R4. Again, equating the real part and imaginary part. By real part, we will get this R1 is equal to R2, R3 upon R4, and from the imaginary part, we'll get the L, that is induction, that is self-inductance of the given coil. L1 is R2, R3, C4, and the cos phi is the power factor of this one. So in this way, we have three bridges, that is Wien's bridge, Schering bridge, and the Maxwell bridge for the discussion of the day. And now we have to discuss about some numerical problems that we have considered in the case of the discussion part, and that is numerical based on the AC circuit. That AC circuit has been already discussed this AC circuit, and on the basis of the discussion of AC circuit, we have some numericals, and these numericals are given. We here consider 10 numericals on the basis of the discussion of the AC circuit as in earlier video. So let us see one by one the examples and its importance. That is example 1. Consider a current is made up of two components, 3 ampere DC component and AC component as 4 sine omega t ampere. So calculate the effective value of the current in the circuit. The resultant current is nothing but sum of DC component and AC component. So we can have the value of 3 plus 4 sine omega t ampere. The effective, that is RMS, root mean square value of the current in the circuit. So for calculating this root mean square value, first we square the current and then taking the mean, and finally we'll take the root. So RMS value has the square and mean. So square mean can be defined as I of t whole square average value, that average is 1 by t 0 to t 3 plus 4 sine omega t whole square dt from the definition, that is 1 by t 0 to t I square dt. So this expression is square expression. So square, that is a square plus b square plus 2ab, in the same pattern 9 square plus 16 sine square omega t plus 24, 9 into 4, 3 into 4 into 2 is 24 sine omega t dt. So we integrate, we can have this sine square omega t is equal to 1 minus cos 2 omega t. So using this trigonometrical transformation, we solve this one is 9 plus 8 is 17. So this is 17. So 9 plus 8, this cos omega t of this sine 24 sine omega t dt. So 9 plus 8 is 17, and here it is 8, and this is 24 sine omega t. So integrating these three factors, we have 17 factor is the finite, and rest of these two factors giving the zero value of the integration, because of this one is the integration, say in the complete circuit, and here it is the in this way cycle. So this value, this value is sine, and here it is cosine, and this value gives the 0 in each cases. So it is 17t divided by t, so the value is 17 ampere square. This is ampere square. Now IRMS means under root of this value, so under root of 17 is the answer. So the effective value of the circuit current in the circuit is under root 17 ampere. So this is the first example. The second example of this is very interesting. The interesting is a house having 220 volt line as usual in domestic purpose. The following three appliances are operating: a 60 watt bulb, 1000 watt heater, and 40 watt radio. In case of radio, you may use the television. So calculate the current drawn by the heater and current passing through the fuse. So the concept of the circuit, suppose this is the house, and here it is the power supply. This power supply is 220 volt. This is RMS value, and there is a fuse in the line. Here it is the fuse line, and three components, that is bulb, heater, and radio, are connected in the parallel to each other. So in each component, the currents are I1, I2, I3. These three currents are flowing in the three components. So the three components are connected as shown in the figure. The power is V into I, and this I is equal to power P upon V, that is power consumed over the voltage, that is 220 volt. So current through the heater I1, P upon V, P is 1000 watt, and this is 220 volt, so 50 upon 11 ampere. Current through the bulb, that is P upon V, 60 upon 220, 3 upon 11. The current through the radio I3 is P upon V, that is 40 upon 220, 2 by 11 ampere. Applying Kirchhoff current law, that is in the circuit, the incoming current is equal to outgoing current. So outgoing currents are sum I1, I2, and I3. 50 by 5, 11, 3 by 11 plus 2 by 11. So it is 55 by 11, that is 5 ampere. So in fuse, this fuse is there, that is the just after main, that is P, and here it is 5 ampere current is flowing. As usual, we have this case is. Now the current by the heater is 50 by 11. The current is this part is 50 by 11 ampere current is flowing through the circuit. So this one is the interesting case, and it is the very practical case that is we have used. Now the third example is for the connectivity. That is, we know that there is a carrying wire has a capacity, and one part is the wire, other part is the earth. On the basis of that concept, there is another example, that is third. Third example is as a 200 kilometer long telegraph wire has a capacity 0.014 microfarad per kilometer. If it is carry an alternative current of 50 kilohertz, what should be the value of the an impedance inductance required to be connected in series so that impedance is minimum? Draw the sketch of the current variation as frequency is changed from 40 kilohertz to 60 kilohertz. So minimum, the word is minimum impedance. The minimum impedance means at that particular frequency, there is a case of resonance. So we have to use the resonance case solution. The total capacitance is given by 200 kilometer, and each kilometer has this much. So 2.8 microfarad be the capacity of the wire. The minimum impedance, that is omega L is equal to 1 by omega C. So L is equal to 1 upon 2 pi F square C, and this is 0.36 millihenry. So this one is the minimum value of inductance that is required. At a resonance frequency, that is omega 0 is 50 kilohertz, the current is maximum, and either side of the resonance frequency, the current will decrease. The variation of the current is shown. So the variation, that is 40 kilohertz and 60 kilohertz, that is omega is less than omega 0, and here omega is greater than omega 0. This value is omega 0. So the variation, nature of variation is very simple. That variation is the same as the variation of current in the inductor circuit. So the fourth example is similar, a simple example, that is a LCR series circuit has L is 10 millihenry, R is 3 ohm, and C is 1 microfarad connected to the source of 15 cos omega t volt. Calculate the current amplitude and average power dissipated per cycle at the frequency that is 10% lower than the resonance frequency. Mind it, the resonance frequency is omega 0, that is 1 upon under root LC. So that we have to solve, and it is the 10 kilohertz. This is the resonance frequency. Now 10% less frequency will be omega 1, and this omega 1 is 10 to the power 4, that is 10 kilohertz minus 10%. 10% of 10 kilohertz is 1, and that's why it is 9 kilohertz. So we have to calculate the value at 9 kilohertz. So the frequency at this frequency, that is 9 kilohertz, XL, the impedance of inductor, that is 9 into 10 to the power 3 omega L, and this is 90 ohm. And the impedance across the capacitance, that is 1 by omega C, and this is 111.11 ohm. So the impedance of the circuit is Z. Z is this R square plus XL minus XC whole square. So R square, that is 3 omega square, 90 minus 111.11, and that is 21.11 whole square, and it is 9. So it is 21.32 ohm be the impedance of the circuit, which is 10% less than the resonance. So current amplitude I0 is E0 by Z. E0 is 15 volt. This is 15 volt, and here it is 21.3. So the current is 0.704 ampere. Average power, that is half E0 I0 cos phi. Cos phi is R over Z. R is 3. Z is 21.32. So it is 0.141. So cos, this is average power is 1 by 2, 15 into 0.704 into 0.141. So this is 0.744 watt. That is the power consumed in the circuit. So the fourth example is based on the simple concept of the circuit, that is a 750 hertz 20 volt source, that is 750 hertz and 20 volt source. This source is connected to the resistance of 100 ohm, 0.1803 Henry and 10 microfarad in series. Calculate the time in which resistance, that is thermal capacity, is given 2 joule per capacitance will get heated by 10 degree. So time, we have to calculate the time. So within that time, it will increase 10 degrees centigrade. So the impedance of the given circuit is as simple as given Z is equal to R square omega L minus 1 by omega C whole square. So after taking these values, we can have this impedance, and this impedance is 835 ohm. Now the power is IRMS cos phi is R by Z, that is 100 upon 800, this 35. So the power, that is ERMS square over Z square into R. So substituting value, and we find the power consumed in the circuit is 0.0574 watt. Now the heat produced in resistance, that is 2 joule per second into this 10 degree. So that needs the 20 joule. So how much time? P is E by T. So time T is equal to E over P. So 20 joule divided by 0.0574. So 384 seconds is required to raise the temperature of the capacitor by 10 degree Celsius. So this is the point. The sixth problem is the mysterious problem that we have to find out something. So a box containing LCR produce 1 ampere current on the application of 250 volt DC supply, when an AC source of 250 RMS at 2250 radian per second is connected. A current of 1.25 RMS flow, means on the DC it is 1 ampere current, on AC it is 1.25 ampere. It is observed that the current rise with frequency and becomes maximum at 4500 radian per second. So find the value of the component LCR. You see, in DC there is a current flow. It means the circuit has the connectivity, and that connectivity circuit has the resistance. So for the DC, resistance is 250 upon 1. So this is 250 ohm. Now on the AC, the current is 1.25. Means there is some bypass through which the current is also flowing. So in case of the AC, this impedance of the circuit is V upon I, that is 220 volt upon 1.25 ampere. So it is 200 ohm. Means the impedance, AC impedance is less than DC impedance. This point is very important. Here it is 250 and here it is 200 ampere. So this indicates that there is some parallel combination. There is some parallel combination. That is, final impedance is less than the one of the component. It means there is a parallel combination. So this one is the circuit, which is the using the parallel combination of the circuit. So the impedance is expressed as 1 by Z. That is, you see, Y is equal to Y1 plus Y2. Y1, this, suppose any one of them, you can say this is Y1 and this is Y2. So this Y is equal to 1 by Z under root 1 by R square plus this omega L minus omega C, 1 upon whole square. So 1 upon 200 square, that is Z, is 1 R square, that is 1 by 250 square plus this is 1 upon omega L minus omega C whole square. So 1 upon omega L upon omega C whole square can be obtained. This is the solution, and this is the 9 upon 10 to the power 6, and this is 9 upon 10 to the power 6, that is solved. So we get that is omega is 2250 radian, 2250 L minus 1 upon 2250 C, that is capacity, is 1000 by 3, 1000 by 3. So what we find? We find that 9000 C minus 1 upon 2250 C. Why it is 9000? Because you see at the resonance omega square is 1 by LC, where omega found as 450 because it is given that 4500 the Beacon maximum. So the rise frequency became maximum is it is the resonance condition. So resonance case, that is omega square, 4500 into 4500 is L. This L is equal to 1 by C. So this value, this can be 2250 L. 2250 L can be expressed as 1 upon 9000 C. So this is 1 upon 9000 C. So the value of 2250 L is equal to 1 upon 9000 C minus 1 upon 2250 C is equal to 1000 by 3. So from there the C is 1 microfarad. C is 1 microfarad. If C is 1 microfarad after solving this equation, so L is equal to 1 upon omega square C. Omega square is 2250 into 9000, that is 45 whole square into 6. So 4 by 81 Henry is L, and R is already calculated, that is 250. So in this way we can solve this equation number 6. Now equation number 7. The example 7 is again very interesting. The circuit draw a power of 550 watt from a source of 220 volt at 50 hertz. The power factor of this circuit is 0.8 and the current lags behind the potential difference. To make the power factor of the circuit as 1.0 means increase the power factor, what capacitance will have to connect with it. So in this way the two concept is simultaneously is current lag. Current lag, where it is current lagging? Current is lagging when there is an inductor, with the resistance L and R. So only in these cases the current lags with the voltage. So the current lags behind the potential. The circuit contains resistance and inductance, definitely L and R. So power average is this much, ERMS, IRMS, and this is the cos phi, is cos phi. So IRMS is ERMS by Z. So ERMS square Z over into cos phi. Substituting the value, ERMS is 220 whole square, power is 550 drawn, and power factor is 0.8. So this Z is 70.4 ohm with the impedance. Now the power factor phi is 1 by R by Z. So R is equal to Z cos phi. So R is 70.4. This is Z into 0.8 is 56.23. So this value of R. So in this way we find out the, by use of inductor L, Z is equal to the impedance of the given circuit is R square plus XL square. So Z square is equal to R square plus XL square. So XL is equal to impedance part is Z square minus R square. So this is the 42.2 ohm is the XL. Now by connecting C in the circuit, the cos factor, cos phi is equal to R over R square plus XL minus XC whole square. And we have to increase the power factor from 0.8 to 1. So for the given cos phi power factor, as it is 1, we have this one is R over R, because XL is equal to XC. When XL is equal to XC, this factor is 0. This factor is 0, and that is under root R square, that is R. So this is the possible one in whole. This R over R is 1. Thus, omega L is equal to 1 by omega C. So C is equal to 1 upon omega square L. So this value omega L. So this is the 50 hertz, 2 into 3.14 into 50 into 42.2. This is the L, impedance of L. So on solving this value, we'll get the C is 75 microfarad. So in this circuit, if you want to increase the power factor, then you have to add a capacitor to the circuit, and that make the some power factor 1. Now the question 8 is, a series circuit consists of L, R, C. The applied voltage and current at any stand are given by, this is ET is equal to 141.4 cos 3000 t minus 10 degree, and IT current is 5 cos 3000 t minus 55 degree. This is the 5. The inductance is 0.01 Henry. Calculate the value of R and C of the given series circuit. Now the resultant phase is 55 minus 10, so 45. That is voltage is ahead through the current, means there is some LCR circuit. So tan phi, that is 45, is 1, that is XL minus XC upon R. So XL minus XC is equal to R. So on this value we can substitute R. So Z is equal to R square plus R square, so under root 2R, and Z is E by I. E is given 141.4 upon 5. 5 is this I amplitude, I naught. So this is 28.28 omega. This is it. Thus under root 2R is 28.8. So R, the value of R is 20 ohm. So resistance is 20 ohm. So we find this one is the resistance. Now we also have the equation, that is XL minus XC is equal to R. So omega L minus 1 by omega C is equal to R. And this value omega L is given, that is 0.1. And thus from this omega L and 20, we can calculate the value of C, this capacitor. By using this formulation, the C is this much, that is 33.33 microfarad is the capacitor that is used in this case. Now the example 9. In this example, we have considered another aspect, that is a 100 microfarad capacitor in series with 40 ohm resistor is connected to a 110 volt 60 hertz power supply. So this kind of power supply is in USA. Americans domestic supply is of this standard. So what is the maximum current in the circuit? What is the time lag between the current maximum and voltage maximum? This is the important feature that we have to find in this case. So solution, in the RC circuit, the peak current is expressed as I0 is equal to E0 upon Z. Z is R square plus 1 upon omega C square, because the circuit is R and C. So this is under root of RMS, and substituting this value, so current is 3.24 ampere. This current. In RC circuit, the voltage lag behind the current by a phase phi, and that phi is Xc by R. So Xc by R 1 upon this value, and this is the 40. So this is phi is equal to 0.6635, and this phi is tan inverse of this value, to 33.54 degree be the value. So the time lag is given by T. Time lag is given by T, phi by 360 into T. So phi is 33.56 by 360 into T, 1 by 60. Time is 1 by n. It is 60 hertz. It is 60 hertz. So this T is equal to 1 by n. That is 1 by 60. So after solving, it is 1.55 millisecond, because it is 10 to the power minus 3. So this one is the equation example. This one is example 10. In example 10, we try to find out the complete concept. That is, a LCR circuit with L is 0.12 Henry, C is 480 microfarad, and R is 23 ohm. This R connected with the power supply 230 volt with variable frequency. Find what is the source frequency of for which current amplitude is maximum, I maximum. Power absorption is maximum in one cycle. Maximum power for which the frequency of the source is the power transferred in the circuit, that is half power at resonance frequency. What is Q factor? When the Q factor. So all these things that we have to discuss. Solution: this current amplitude I0 is given. This is I0 is E0, this R square plus omega L minus 1 by omega C. At resonance, this value. So resonance frequency is 4167 hertz from this part. So F is equal to 663.5 hertz. This is, here it is, you can say radian per second. So now I is E0 upon R, that is under root 2, here it is, this is under root 2 E RMS by this. So this value can have the current, that is 14.14 ampere. So the first part is the maximum, that is a maximum amplitude of current is 14.15. Why it is maximum? Because the variation is something this. So this value is I0, that is maximum. The average power absorbed by the circuit is given by P, ERMS, IRMS cos phi. So ERMS into RMS, this is maximum, this value is equal to 1. So ERMS by 2, so 2300 watt at the resonance frequency, that is 4167 hertz. And remaining part is the given as the half power frequency are the frequencies at which the power in the circuit is half the frequency power. These are given by omega 0 plus R by 2L is 4167 plus minus 23 upon 2 into 0.12, that is Henry. So this value is 40 4260 radian per second or 4071 radian. Means one time it is positive, so this value. So if it is negative, so this value. Means this kind of the things is, this kind of thing is, that is there. Here it is omega 1, this is omega 2 and omega 0. So this omega 1 is 4071 and omega t is 4263. The current amplitude at this frequency fall to 1 by under root 2. That is the current. This is I0. So I0 by under root 2. This part of the current. Resonance. And this value is 10 ampere. So this value is, here it is 14.14 ampere, and this is 10 ampere. This is 10 ampere. The quality factor is given, Q is given as omega 0 L by R, quality factor of the circuit. So this omega 0 is this is the omega 0, that is 4167. 4167 into 0.12 upon 23, so 21.74 be the quality factor of the given equation. So these are the examples that we have to consider here in case of our discussions. So this is all about the problem that we have discussed in the case here. So what we find, we have part one. The part one of this video is AC circuit, and the part two is AC. This is circuit, and this is AC bridges, and plus 10 numericals. Without numericals, there is no solid improvement of the concepts. So these numericals are very important for the further discussions of the cases. So this is all about the today lecture. Thank you very much. On the next video, I would like to discuss about the network analysis. Thank you.